Okay, we start today's session, and the first speaker is Lars. Lars, please, you're online.
Okay, thank you. First of all, thank you for inviting me, giving me the opportunity to speak. I just noticed that since I'm giving this from my iPad, you won't be able to see me while I share my screen. Okay, that's not and I also have to warn you that I have my little daughter here in the room next door. We didn't have a plan B, so it's, I hope it's going well. Anyways, so let me start sharing my screen. Again, thank you for having me here. I'm actually quite excited to give this talk, and it's already 1 year old because it was stuff that we did. Yeah, essentially we worked on this until last year. So by the way, can you see my screen now?
Yes.
Okay, good. And so it is about charge and heat transport in a charge 2-channel condo device. And so let me first of all just introduce my collaborators. So I had essentially 3 collaborators on this. Andrew Mitchell from Dublin. So he's an expert on NRG, numerical renormalization group. So everything that is numerical renormalization group in this presentation is he did it. Then there's Eran Sela from Tel Aviv University. And then there's also Gerwin van Dalem, who was my PhD student. So he essentially defended last year, but he made most of the actually complicated calculations. And so this talk is based on 3 publications. So we had there was a first part which was only about charge transport, and then we had. So can you see this pointer? Yeah, I think you can see it. Then there's this PRB, which is mostly about heat transport, and then there's this last paper, which is a very technical version of the first 2. So if you want to have all the details, all the calculational details, that's the paper you should have a look at. Okay, so let's just start with how we came into this business. So what you see here is, so this is taken from a paper. This is an experimental setup of a device which was fabricated and also analyzed in Paris in the group of Frédéric Pierre. And so they wrote a beautiful paper which was published in 2015. And this was also actually when we got interested in this problem. So I should say that we were in no ways involved and at no stage involved in any type of experiment here. And I'm saying that because I will talk a bit about experiment, and I don't want to give a wrong impression. So we did theory, that's it. And we're also not part of this paper. Okay, but it was this paper that motivated us to look into the problem. Okay, so since I looked at the program and I didn't see a lot about Kondo physics, so I thought maybe I give you a very, very quick reminder. So Kondo physics, it's about the physics of a single spin, or as we will later see, in fact, a degenerate, a twofold degenerate system also does the job. And it is coupled to a bath, like in that case, fermionic bath. And this fermionic bath couples with its spin degree of freedom here. It couples antiferromagnetically to the spin. And so this is a very old problem. In the end, after many years of research, people understood that at 0 temperature, the spin is screened, and there's there's many things you can do in this problem theoretically, and one thing which will be useful later on is often in the context of the Kondo effect, you will see the usage of a renormalization group. And so what you see here is a very simple flow diagram. So it describes the flow of the coupling upon reducing the energy scale. And basically what you see here is that upon reducing the energy scale, a small antiferromagnetic coupling, it will grow indefinitely. So essentially it will explode, the problem will become a strong coupling problem. Yeah, and then eventually, like this is not part of this RG picture, but eventually people figured out that at strong coupling, the spin is screened. Okay, so much for the like single channel. Let's call that single channel Kondo effect. Now, this talk is about the two-channel Kondo effect. So this is a variant of the single channel Kondo effect or Kondo model, and it is a generalization in the following sense. So we assume that we now have two fermionic baths, and the spin degree of freedom, so the local spin degree of freedom of the two fermionic baths is again coupled to one single spin. Okay, so this is the Hamiltonian here that describes this situation. So we have a bath on the left-hand side, bath one, bath on the right-hand side, bath two, and both of them, they couple to this spin degree of freedom. It's very important here. I will come back to that later. It's very important here that we do not allow electrons to essentially, or we do not allow mixed spin densities here. So we do not allow something like an electron from the left and an electron from the right to couple directly to the spin degree of freedom. Because as soon as you allow these terms, you will go back to one channel Kondo. This is also, if you want, this is one of the main obstacles in like experimentally realizing the two-channel Kondo model. Okay, yeah, I mean, I already said it. There are these, there's this local spin density, and again, like what I just said, there's no L dagger sigma C term. Okay, so this version that you see here is the so-called isotropic two-channel model, and the reason it's called isotropic is because all the spin components, they couple with the same coupling. So this is yeah. Now let me, okay, and this is actually a very complicated problem. Like theoretically, not only, I mean, I mentioned experimentally it's super hard to realize, but also theoretically, it's a hard problem. And I want to first use this RG picture that I just introduced to describe some of the physics of this model. Okay. So what you see here is this is a generalized flow diagram. So before, remember, I had this essentially, here it was. I had this one-dimensional flow, so just runaway flow. Now I have two couplings, and I'm just doing the same procedure. I'm saying, okay, I'm reducing my cutoff, and I'm asking, where do my couplings flow? And so upon doing so, like what I pretend to do now is I pretend to do a one-loop renormalization group calculation. And this is in fact the picture that you find. So you find that, I mean, first of all, we have these two lines. These two lines are very simple and very easy to understand. Like this line is when JR is 0, then we're back to the one channel problem. This line is when JL is 0, we're again back to the one channel problem. It turns out there's a very special line in this problem. And this very special line is when both couplings are exactly the same. So this is this white line. And on this white line, there's a very special point. It's like, I mean, this is the RG equation that describes it. And there's a very special point. And this special point is a critical point. Like, unfortunately, this critical point is not located. So it's located at a dimensionless coupling JC is 1, so it's not at weak coupling. So so there are so a priori there are not like there are reasons to distrust this this result, but it turns out like people did a lot of things, much more complicated things later on, much more sophisticated, and this critical point actually stood. So this is like even though we learned that we shouldn't extend like these renormalization group calculations to when couplings are 1, this critical point actually stands. So there is a critical point, and this critical point, yeah, it essentially separates this half plane to that half plane, where like if we're inside here, we have runaway flow towards strong coupling with JL, and if we're here, we have runaway coupling flow to JR. So let's maybe try to let's try to understand in more physical terms what's going on here. So yeah, so let's just consider the following situation. So we have a chain here, and like the spin density or of this chain, of the last side of this chain, it couples to this spin, and we have the same on the right, and they couple with 2 different couplings. Now, if one of the 2 couplings, let's say JL, is much stronger, so what's happening is that eventually this chain, it will grab the spin and will screen it, and this chain here will effectively decouple from it. So we have a flow to strong coupling, and we have a 1-channel effect. Same obviously is true if JR is greater. So there's yeah, that's just but now what's very special is when JL and JR, when they're equally strong, and this is a situation in which we have a frustration in the system. So, and the frustration is like this chain wants to grab the spin, and this chain here also wants to grab the spin. So they both try equally hard, and like you could imagine now, like that you end up now. So you're combining 3 spins, a half. Say you have a residual spin a half, and now you can ask, once I have this, I'm looking at this compound now and how it is coupled to the rest of the chain, you find it will be again ferromagnetically coupled with the antiferromagnetically coupled with a modified coupling, and they will be equally strong. And you can iterate that, and this thing will actually never break. So this is a situation. So it will go through the whole chain, and there will always, no matter how many sides you couple, as long as you couple them equally strong, there will always be a residual antiferromagnetic coupling, which is exactly the same on both sides. So in fact, this if you want frustrated like critical point, this frustrated fixed point is often called a non-Fermi liquid fixed point, mostly because it has a phenomenology which is not exactly Fermi liquid. For instance, you have like logarithmic corrections, but there's also another quantity which is very interesting in this context, which is called the impurity entropy. So the way an impurity entropy is defined is you take the system with the impurity and you subtract the system without the impurity. And so it turns out, I mean, this is nothing you can see from my discussion here, of course, but it turns out that this is 1/2 log 2, or if you want, half a spin, or half a fermion. Okay. Okay, good. So are there questions up to this point? Okay, doesn't seem to be the case. So in any case, please interrupt at any time, as soon as I say something which isn't totally clear. Okay, now there is it turns out that there is a type of Toulouse point in this problem. So the single channel Kondo problem has a famous solution, which is called the Toulouse point solution. So it's a solution where you can solve it exactly. It's a point in parameter space where you solve it exactly. It turns out this model here has the same type of Toulouse point, and this was found. So there was actually a lot of activities beginning of the 90s, and it was Emma and Kivelson, and they found that there is in fact a point in parameter space where you can exactly solve the problem. Okay, so it's a very non-trivial. It's a very non-trivial solution. So it works with essentially what you're doing is you're starting. So you start with your system, with your Hamiltonian. You have your bath, and then you notice that since you have rotation, like isotropy, you can map the problem to one-dimensional problems. So in fact, just like I showed you, two chains, one spin interacting with two chains. And then you go through a bosonization procedure. So you go through a bosonization procedure in this bosonized language. You can then manipulate, like you can manipulate your spin degree of freedom and your bath in a way that eventually you can re-Fermionize the problem. And once you have re-Fermiionized the problem, you find that at a very, and there's actually one point in parameter space. So I'm not giving you the exact numbers here, but what's important is it's anisotropic. So it's not the isotropic Kondo model now, it's an anisotropic Kondo model. And at this specific point in parameter space, you end up with the resonant level model. So you end up with the model where you have one level, which is resonantly coupled to a bath of electrons. And it's a peculiar one. It's one of Majorana fermions. However, I mean, as I said, it's exactly solvable, so it's quadratic. And the fact that it is Majorana fermions also naturally explains why we have this impurity entropy, which is 1/2 log 2 or log squared of 2. Okay, and the way it looks is like this. So you have a bath degree of freedom here, and I should point out, like in this fermionization procedure, or like bosonization fermionization procedure, we end up with 4 baths. So this is not very surprising, because we started with 2 leads, and both leads have 2 spin degrees of freedom. So which is kind of like 4, yeah. So you have 4 baths if you want. And you also end up now with 4 fermionic type degrees of freedom. But there's something very important going on here. And what's important is that there's only one of them, this what they call SF, which couples to the spin degree of freedom. So what's happened to the spin degree of freedom here during this mapping is that at some point, the spin degree of freedom was rewritten. So because the spin degree of freedom has 2 states, it was rewritten as a single spinless fermion. Okay, and this is this one, and here you see very nicely that only here the linear combination with the plus, and here the linear combination with the minus, they couple. And now you can rewrite all of this. So these are still actual fermions. And now you can go ahead and rewrite this in terms of Majoranas. And then you have your Majorana resonant level model. And also here, what you see, this is a detuning parameter, delta E. So for a spin model that we discussed, this delta E would actually correspond to a magnetic field, because it would split the degeneracy. Okay. Any questions so far? So yeah. Okay. So maybe you all know the story, anyways. So if you want, for instance, it's textbook material by now. It's explained in in Giamaki's book. It's also in the Cvelik book. It's explained very nicely. But the paper itself is also nicely readable. Okay, so now let's go back to this flow diagram. And so it turns out now that I didn't make a huge point of this, although I mentioned it, but this flow diagram actually is only valid for isotropic couplings, but this Emery-Keevelson fixed point, this Emery-Keevelson point where you can solve it exactly, is in fact one with the finite anisotropy. However, it turns out that from a point of view of renormalization group, this anisotropy at this critical point, now I call it NFL point, is in fact irrelevant. Okay. And this is quite important because it will allow us to calculate asymptotic quantities at this Emery-Keevelson point to get leading order results. And then depending on whether leading order is good enough or not, one has to do something on top here. Okay, good. Now, let's see. So now we have this two-channel Kondo model, and there's also this, I already mentioned this in passing, but I wanted to make that point. Like as soon as these two baths, they talk to each other directly in this manner, you can effectively, you can quite easily convince yourself there's always a rewriting then with the linear combination of both baths, which allows you to write the problem as an effectively one-channel problem. So, and this is in fact at the heart of why experimentally it is extremely hard to realize that model. And yeah, basically many so people have tried for 20 years now, and also one has to say they made surprisingly, they came quite a long way. So, for instance, there was one realization by the group of Goldhaber-Gordon, which is basically 10 years ago, and where the setup was done in the following way. So there was a quantum dot, which was which provided the spin degree of freedom, and then there were two leads, here and here, and like a third lead, which was actually interacting, and it had meaning you could fix the occupation of that lead, and that effectively allows you to suppress this coupling to a very, very good extent. Okay. Now, I also already mentioned that there's also like even though I talked about spin so far, we don't have to take this spin too seriously. Like the requirement to observe this Kondo physics is in fact not to have a spin degree of freedom, but to have like a two-level system. General. So that came in the mid-90s to propose a version of the two-channel Kondo model, which they call charged two-channel Kondo model, for reasons that will become clear in a second, I guess. So, and there the ingredients were the following. So instead of, I mean, usually when people try to model Kondo physics or Kondo, like when they try to model Kondo systems in such a mesoscopic system with quantum dots, they're actually trying to make small dots. Now, what Matveev and Furusaki, what they suggested was to take a large dot with the continuous spectrum. I will tell you why in a second. Also, what's important for that setup is that you actually get rid of the spin degree of the fermions. So and the way to do that is by applying a large magnetic field. So in the experiment that I will talk about later in a bit more detail, this was, for instance, for Tesla magnetic field, and then these leads they were in the quantum Hall regime. Okay, but let me try to walk you through the mapping in a bit more detail. So the way the mapping proceeds is as follows. So we have this setup, we have leads, we have this central region, we have this constriction with tunneling, and we have gates with which we can control the filling of the dot. Okay. And now and again, important, the electrons, they do not have like a spin degree of, so we have gotten rid of the spin degeneracy by applying this large magnetic field. Okay, now the mapping goes as follows. We start by essentially saying, okay, we can label the electrons with their positions, and we call spin up when the electrons sit in the lead, and we call spin down when they sit on the dot. So that's the first one. Now, what's the role of the gate? Well, the role of the gate is as follows. So with the gate, we can control the filling. This gate controls the filling on the dot. In fact, this will be our spin degree of freedom, because if we control, like if we think of a system with the charging energy, then you've probably all seen these parabolas which tell you what the energy is of a specific number of, like the electrostatic energy of a specific number of electrons. Now, by tuning this gate voltage appropriately, you can get into a position where it's energetically equally good to have capital N or capital N+1 electrons on the dot. So, and this is a proper degeneracy, and this is what will be our pseudo spin in the problem. So there will be a pseudo spin in the problem, pseudo spin capital S, and spin down, we identify with having N electrons, and spin up, we identify with having N+1 electrons. Okay, and now, and this is an important point. Like we have to somehow cut the dot, and the reason is we want to be able to separate left from right. And the way this is achieved in the experiment is they put a massive decoherer on top of the quantum dot, which essentially means that the electrons on the left and the right, they forget about each other. So basically, we can introduce a new quantum number, which is electron sits on the left or electron sits on the right. And now we have electron on the left with spin up and spin down, and electron on the right with spin up and spin down. And you can already guess these will be the two channels, of course. And also just to illustrate how an effective Kondo Hamiltonian comes about now, like what you can do is you take an electron, so it's path one now. You can take an electron from the lead and you put it on the dot. So basically what it does is it changes this pseudo spin, because you actually, no, this is, I think, okay, what I'm drawing here is actually the other process, but anyways, so let's say I remove an electron here and I put it there. What I will do is I will also change, of course, the spin here, because I'm changing N. N goes down by 1. So if I was in N+1, I go to N. And I can turn it around. So there's the Hermitian conjugate process. And the same is possible here. Okay, so now we have this effective model, which is not quite the two-channel Kondo model, at least not the isotropic one, but it's actually the maximally anisotropic one, because it only implies this J perp, and we don't have J set terms. Okay. For those of you who have a bit of experience with Kondo type problems, they know that this is not a major thing, because it's well known in the one channel case, and this is also true here, that renormalization processes, they will in fact induce these SZ type terms, these diagonal terms. So under renormalization groups, JZ terms, they are created, and eventually, like Kondo systems, flow to isotropic situations. So, and this was also pointed out in this paper by Affleck, where he essentially said that at the two-channel Kondo fixed point, the anisotropy is irrelevant, which means that in fact this system, although it doesn't look like an isotropic Kondo model, two-channel model, should be described, or like it should flow to the same critical point. Okay. And that also means that to leading order, we should be allowed to use this Emery-Kivelson type of calculation. Okay, are there any questions up to here? Okay, doesn't seem to be the case. Like, unfortunately, since I cannot see you, can somebody maybe just let me know that you're still around?
Yes.
Okay, good.
Yes,
Yeah,
we're still around.
Okay, very good. I was just worried that somehow the connection broke, and I'm doing this just for myself. Okay, it's really not ideal with the iPad. Sorry for that.
You see in the down corner, right down corner, the number of people, online people, that shows you that people are still listening.
Yeah. But I also don't see that in the share screen mode. So I basically see nothing but the slides. Okay. Anyway, I know you're here now. This is good enough for me. So yeah. So basically, what I'm showing you now is how one can use now the properties of this Emery-Kivelson point to calculate a couple of things, and also not to calculate some things. So what I will show you is that we can quite nicely calculate the crossover from the two-channel physics to one-channel physics. And this one we can do because like all anisotropies are irrelevant, and the flow from Emery-Kivelson to the strong coupling is determined by a relevant parameter that we know and that we can treat essentially exactly within this Emery-Kivelson framework, which also means we get like extremely good agreement with be it like, for instance, numerical renormalization group, which is an like numerically exact method to do this. But there's other things, like for instance, I told you there's these there are these anisotropies, and they correspond to irrelevant corrections, and those are not part of Emery-Kivelson. And then there's two things one could do. One could do perturbation theory in this anisotropy parameter, which is actually, yeah, you can do it, but it's very hard. And it's also, it leads to very high order diagrams. But apart from that, there's also prefactors that we don't know. Okay. All of this is not an issue for NRG, because NRG can just take the model and go about it. Okay, so let's talk about the experiment for a bit. Let's see. So I advertised in the title we do charge and heat. So basically, yeah, we can look at these relations. So we can have a bias voltage, we can have a bias temperature, and we have currents here. And the quantities I will be looking at will be the conductance and the G and the thermal conductance kappa, and they are related to these correlation functions here in the standard manner. I mean, this is not unique to this setup. These are just standard relations. And also one thing I will discuss is the Lorentz ratio, which is important for the Wiedemann-Franz, for the Wiedemann-Franz law. Okay. Now, this Emery-Kivelson solution is funny in the in one sense, which is that concerning a voltage bias, you can actually do exact calculations. And the reason for that is simply that the mapping of the Emery-Kivelson, like the mapping which leads to this Emery-Kivelson solution, it does not break down once you include a finite voltage. And the current operator is relatively simple. That's the charge current operator. So it essentially involves two of these Majoranas. So B is a Majorana now, and this is also a Majorana fermion. The heat current operator, on the other hand, is quite involved. It's a complicated object, and it should also not be surprising that it's more complicated, because it involves essentially all the degrees of freedom, which the system possesses. So you see like psi f, psi sf, psi c, psi s, and B and A, which are the two Majoranas. So that's, yeah, not surprising. Like all of the degrees of freedom which were involved in the mapping, they show up here. But that's one complication, but there's another complication, which is that those are also like higher order correlators. So these are relatively simple still, and these are higher order. So for this, we have to do linear response. So we could, there's nothing exact you can do with these, whereas this one you can do exactly. Okay, yeah, so this is what I just said in words. Now, what I'm showing you here is, so this is the experiment, and what you see here is this is just charge for the moment, charge conductance as a function of T over Tk. So Tk is the Kondo temperature. That's basically the temperature where the coupling goes to 1. And in this curve here, you see dots, triangles, crosses with various axes. And underneath, you see a dotted line, and all the dots, etc., crosses, they are experimental data, and the dotted line, that's our theory curve. But okay, this I already explained, but let me first say something about these experimental curves. So what's really remarkable here, and I mean, this is like, I've never seen anything like that, is that in terms of T over Tk, this experiment, this conductance experiment, actually covers 10 orders of magnitude. So this is like, or maybe not 10, 9, but okay, it's massive. Like it's a huge range. And it is, yeah, I think, to my knowledge, it's one of the most impressive, yeah, curves, like showing critical properties that I've seen. Now, let me say one thing. So in the paper, there is a point where they say this is the universal conductance curve at the critical point. So by what they mean by universal is the following thing. So here we see different conductance curves, and they are for different systems. So different systems, D here is for instance, a bandwidth or a cutoff. So they're different systems, and you can already see they look very similar in shape, but they're shifted with respect to each other. Now, universality basically means if I scale temperature not with respect to this bandwidth parameter, but with respect to the Kondo temperature of the individual curves, I should expect to be able to collapse all of these. So that's what universality is. Okay, so now in fact, there's two strategies in which you could measure such a curve. One strategy is, yeah, you just measure it. You take your system and you measure it. It turns out that this is impossible. Like, this is just impossible, because yeah, there's like the experimental setup as it stands, it actually only allows for 1 order of magnitude in temperature. In like it essentially the way they set up the experiment, they can go from roughly 10 millikelvin to roughly 100 millikelvin. Because if they go outside this range, they get in trouble with charging energies, etc.
Can I ask a quick question? So my question is, why is this curve, this transport or conductance curve as a function of temperature, why is it so wide? When here it's like the width is sort of like 3-4 orders of magnitude, and what you earlier showed the results even more. So why is this such a huge temperature scale over which there is a change? And what sets this width? Can perhaps I missed that? Yeah, why you have such a broad feature?
Well, this is, I mean, first of all, this is logarithmic scale, of course.
Sure. But it's across many orders of magnitude. But if I, for example, I'm a cold atom person, and if I see when I have a phenomenon like Bose-Einstein condensation, yeah, from going from 0 condensed fraction to let's say 80% or so, this change, you just have to change the temperature by a factor of 2 or by a factor of 4, but not by an order of magnitude. So why is this so, I
mean, this is because we measure everything in terms of TK here.
Yeah, okay.
I think this is just, I mean, it's like if you were to measure it in one, let's assume you could do that, you would measure it in one device, it would not look like this. I mean, it would look like a sharp feature.
Okay.
So it's really the fact that we scale everything with TK. And it's exactly TK which sets the width.
Okay, apparently, yeah. Okay, good, thanks, yeah.
Yeah, sure. Thanks for the question. And then, I mean, as I said, they simply cannot do that. So what they did is something slightly different. So they basically, essentially measure at the same temperature, but they do it in different systems. And one of the really, really nice features of this setup that I showed you is that they have huge control over TK. And the reason is this TK is essentially, this TK has a lot to do with, let's go back here, with the tunnel coupling. And by varying the tunnel coupling, they can vary TK from essentially the bandwidth down to very low numbers, which are on the order of like millikelvin. Okay, so that's essentially their trick. So they have a small actual temperature window in which they can measure, but they can measure for many, many different TKs in a large window. Okay, so basically now what they do is, let's just assume we fix the temperature and now we change TK. So let's say this is, and now this is how we get our curve. Okay, so this is how we can build the curve. If the curve is universal, both strategies should actually give us the same result. So it turns out we tried that, and that was our first attempt. So actually, no, what we did was we looked at one system, because energy obviously doesn't have this problem. Like for energy, it's essentially a piece of cake to do 10 orders of magnitude. But okay, that's just what it is. And then we compared this curve, this universal curve, to experiment. And we saw it was actually quite a bit off. Okay, then we asked ourselves, okay, what's going on? What's the problem here? And so it turns out that if you look more carefully, there's obviously another scale in the problem, which is the bandwidth. And when you talk about universality, and about universal properties, like you always want this ratio here, TK over the bandwidth D, to be essentially 0. However, in the experiment that we're looking at, they measured, since they vary TK in such a wide window, they actually measure in regions, like depending on the value of TK, obviously, but this is not a small number or negligible number. It's actually, it can be a number of order 1 in these systems. And what we then tried was, so you could call this like non-universal parts of the curve. And what we then tried was we simulated the experimental protocol. And we also allowed for TKs, which were on the order of the bandwidth. And then we could, in fact, just going through the experimental protocol, we could fit this curve. And it actually, it agreed also quite well with all the other parameters. Okay. One more word here. We did this with NRG because the Emery-Kivelson, it doesn't work here. Okay. Are there any questions? Okay. If not, I think I have 10 more minutes. So we can also do the Fermi liquid crossover, but I would rather not talk much about it. So this is in fact what one can do with the Emery-Kivelson. So in view of time, I'm skipping that. Like all I'm trying, or I want to show you is what you see here is this is now a comparison of NRG data, which is the dots, to the analytical solution. And you see it fits perfectly. So it fits really nicely. So the Emery-Kivelson solution here really works nicely. Yeah, and this is a comparison to data. I should also say we don't want to take credit for this. This was also already discussed in the 90s, although the energy hadn't been done before. Okay, now let's move to heat transport. Just sorry. Can you give me a second? This is unfortunate. Okay, as I said, I didn't have a plan B. Okay, so heat transport. We are restricted to linear response. Emery-Kivelson, like the mapping with Emery-Kivelson breaks down, but we can use Emery-Kivelson to calculate the linear response quantities. Okay, so we have a free theory. So you would say, probably it's quite easy to calculate like the heat transport, but I also showed you that the current operator looks very complicated. So in fact, it turns out that you have to solve 3-loop diagrams, and there's many of them, but we were quite lucky. Most of them are actually 0. Like a lot of them are 0 or subleading in their temperature behavior. So even though formally you have something on the order of 1,000 diagrams, it turns out it's enough to calculate one of them. Is at least in the limit when t goes to 0, which is what we're interested in. So we want the leading order temperature behavior. Okay, so we do the calculation and of the heat current linear response again, and we get the kappa. We get the kappa, which has this form. So it has a brief factor pi squared kb squared over 6h times t. Okay. You might not remember, I didn't make a huge point of it, but the conductance was actually given by 1/2 e squared over h. So let me just go back. So yeah, here you can see it. This is the NFL fixed point conductance. It's 1/2 e squared over h. And now we can do what we often do. So we look at the Lorentz ratio, and we find that although people call this fixed point always the non-Fermi liquid fixed point, it actually obeys the Wiedemann-Franz law. So we in fact we get a Fermi liquid type result at the non-Fermi liquid fixed point, which yeah, I think there's like the Wiedemann-Franz law is in a way it's not a law anyways, so there's nothing wrong with this. But we just thought it was funny that at the point where people usually say it's a non-Fermi liquid, you get a Fermi liquid type result. Okay, in fact we wanted to look at the Wiedemann-Franz law along the Fermi liquid crossover, but it turns out that this is technically very hard, and this is also where many of these, like I told you, there's many of these diagrams, and almost all of them are zero, but along this crossover, a lot of them come to life. So since Herwin's PhD was running out of time, we didn't do that, or we didn't come around doing that. However, we have the strong suspicion that at the Fermi liquid fixed point, which is when you flow to strong coupling, the Wiedemann-Franz is actually violated. And so there's two reasons why we have this suspicion. So reason one is, like, at an early stage of the project, we were sloppy with the heat current operator. So we, in fact, instead of properly deriving the heat current operator, so you saw it was a complicated expression, we guessed it. And while with this guessed heat current operator at the non-Fermi liquid fixed point, we recovered all the results. We can also extend that one. We can quite easily extend that one to the Fermi liquid fixed point, and there we found a number which was the Lorentz number times 21/5. Okay. Funnily, this is a number which pops up in mesoscopic systems quite often. There's another thing, which is if you look at the Fermi liquid fixed point in this setup, the Fermi liquid fixed point corresponds to a situation where one of the leads completely decouples. So in fact, the connection is broken. So what that implies is there is no leading order result. So the leading order results that are usually somehow coupled via their like quasi-particle character, they vanish, and all you end up with is the corrections. And as far as I know, nothing fixes the ratio of these corrections. So in principle, all bets are off. Yeah, so this is what I just mentioned. Okay, there's another funny thing, which is, I mean, I told you that there's these Majorana fermions, which are important for this effective critical model. There's a result from Cardi and Calabrese from the early 2000s about heat transport in one-dimensional systems. And heat transport in one-dimensional systems has, so they look at the situation where I have two chains and they are different temperatures, and I couple them. And these chains, they are characterized by conformal charge C, which is the same. And then the heat transport is directly proportional to this conformal charge. So in a way, the conformal charge is in a way a measure for the amount of degrees of freedom. So in some ways, it's intuitive that this thing can pop up. Now, if we look at this with our result, and we just try to identify C from this expression, we find that it is 1/2, which is actually the conformal charge of 1D Majorana fermions. Okay, with this, I would like to finish. So one thing to take away is that this device is actually an excellent quantum simulator. In the meantime, they've also done other experiments. So very recently, they did 3-channel experiments, and they're also trying to look at the fractionalization in more detail. And not only that, one can also find a very good quantitative understanding of the conductance. Maybe independent of this device, what I find very interesting is that you have the violation of the Wiedemann-Franz law at the non-Fermi liquid point, and that you have this relation to the conformal charge. Yeah, and with this, yeah, I would like to thank you for your attention, and I think I kept in time, and I'm happy to take your questions. Are you still around? Okay. I can't hear you.
Here is the cube.
Now I can hear you.
Now I see a lot of people online, by the way.
Okay.
In the auditorium, we are just 4, but Vadim wants to ask.
Just a quick question. So the C equal 1/2 theory, which seems to be the critical, the unstable critical point, right? That you are studying, that is obtained when you decouple the other channels. You started off with 4 different channels, so C was equal to 4. Then you said, I can decouple a number of channels, and I end up with C equal 1/2. But even if we assume that it is experimentally possible to measure the heat transport in that system, that would involve all those channels, right? So you wouldn't get
No, the other channels, in fact, wouldn't make it through.
But wouldn't make it through.
Yes.
I see.
So they are there, but they don't contribute, at least not to leading order.
Right. Okay. So they get reflected by the
exactly
by the dot. Okay.
They are there, but yeah.
Okay. And C equal 1/2 is that effectively the, so that's the Ising model. Is that effectively the infrared fixed point at the isotropic unstable?
Exactly.
Okay.
Yeah.
Right. Okay.
Yeah.
And that is known, right? It's a known factor.
Yeah. There is
yeah. Okay. Okay.
Yeah.
Online people? Anybody wants to ask questions from those who are online?
Yeah, I have a simple question, perhaps, or perhaps naive question. So I'm not a condensed matter person, certainly. I'm a cold atom person. And so my question is, do you see a good platform based on cold atoms that could realize this kind of Kondo physics? I'm not aware of it. I think because it's pretty involved. You need basically these leads, you need this dot type, you need this local control, I suppose. So I think it's difficult. Can you comment on that?
I mean, I don't feel competent answering this one because I don't really know what's feasible with cold atoms or not. But I mean, I think one of the, at least from in these mesoscopic systems, the main challenge is that you have to suppress. So essentially, you need two baths. And this is almost impossible to get. So that the best you can do is you can suppress tunneling between the bath or coupling of the bath. And there's these two things that I'm aware of on the market, One is you take an interacting dot, which essentially the reason why an interacting dot is like you need a big dot which has a continuous spectrum, but it should be interacting. And the reason why you want that is you want to make sure that an electron that leaves the dot hops onto your small dot, it actually comes back. You don't want it to go out and then go into the other lead, because as soon as it does that, then you're basically in a one lead situation. So how feasible it is in a cold atom context to essentially isolate two baths and make sure they don't talk to each other, and even like
yeah, my gut feeling is one has to do this with a system where you have, so the cold atom people usually have local interactions, very local, yeah. So tunneling is usually what's happening, and that actually mediates an interaction, second order process or so, tunneling back and forth. It might be what might work is perhaps something where you have some more long range interaction. So either with let's say dipoles on a line where you then couple spins, yeah, so from side to side, so something like this, or perhaps even an ion trap, yeah, where my guess is one perhaps could simulate some of this with ion trap physics. So with these quantum computer type ion traps where you have really local control and you can mimic spin coupling or engineer it in such a system. But I'm not so sure. Yeah, I have no idea. I've not thought about it in any more specific way.
Yeah, probably just a short comment. We shouldn't lose sight of the fact that unlike a condensed matter system, in atomic traps, it is possible to have a pseudospin of an atom which is greater than 1/2, so to speak. So you can work with fermions which have an effective spin equal to 3/2 or 5/2. So I think when Lars is talking about the problems of condensed matter implementation of the system, what he has in mind is always having two baths of fermions, and then it is difficult to separate those. But unlike a condensed matter system, you can have one bath, but 4 spin degrees of freedom in the fermion, and that I think that could be a game changer in the ultra cold context.
Yeah, I mean I think that could also okay. I have no concrete setup in mind, but that could work. Yeah. I mean,
thanks.
Thanks for the question. I also should say that there's one thing which is quite nice with this setup compared to this. I mean, there's these other setups where you have a small dot, and this small dot is your spin degree of freedom, and it's an actual spin. So it's like in the sense of an Anderson model. So it comes with interactions and like an effective spin degree of freedom. While this is nice, one of the advantages of the charge setup is that you have much better control over TK. So you can vary TK in a much wider range. So in this like quantum dot setup, TK is usually very, very small. Du gleich, Maybe, gleich. Yeah. So are there further questions?
Okay, if we don't have further questions, we stop recording, and we thank Lars.
Yeah, thanks for tuning in and letting me speak.